Très bien. I think it's on. You can go on. Please.
Thank you so much.
Yeah, we can see it's recording. Thank you, Mohamed. Thank you, Alex. Okay, so today we are welcoming Diane Larlus. Diane is, well, the title is Principal Research Investigator in Neverlab Europe, so which is a company from the big Korean internet giant Naver that nobody knows in France, I think, but that nobody cannot know in Korea. That's Google Korea, equivalent of Google. And Diane is also leading a chair in the equivalent of Anity in Grenoble called MIAI. You can see the logo on our first slide. Diane is specialist of visual search, and today she will discuss the topic of her chair, lifelong representation learning. And at the end of the presentation, we will have a short session for interacting. I guess we can interact in French, right? Diane is from France as well. So if you prefer to have interaction in French, that's fine. You can raise questions during the talk. I will try to forward the question to Diane during some break that we could find during the presentation. So just ask in the chat. And yeah, and that's it. Thank you very much. Diane, the floor is yours.
Thank you very much, Nicolas. And well, thank you very much for the introduction. And thank you very much for the invitation. I'm extremely happy to be here. And my plan today is to give you an overview of why this problem of lifelong visual representation learning is important. I'd like to at least convince you of that. And also I will show you some of our contributions in that field for the past, well, let's say a year that we've done in this in the context of this MIAI share around lifelong representation learning. And first, I would like to start with, yeah, no? Can you see my slides still?
Here we see your desktop, and now we see your presentation.
Okay, wonderful.
Here, a bunch of cats. Well, now only one.
Wonderful, because I'm going to talk about cats. I'm sorry about that. So first, let's start with some context, and let's consider a typical task of computer vision, the task of image classification. And well, let's in particular focus on one of the favorite tasks of computer vision researchers, cat classification. That's why I have cats here. So let's assume that you would like to build a model that is able to predict if an image contains a cat or not. So first, what you need to do is to collect a collection of images of what cats are supposed to look like, which is surprisingly diverse. Then you optionally can collect a set of images of what cats shouldn't look like. And then you can use all these images to train a model, your favorite model, let's say a convolutional neural network, or something else of your choice with your favorite training algorithm. And once you've done that, you can give an image and your model is able to predict if the image contains a cat or not. And that very simple recipe works extremely well and allowed to build very strong classifiers that are able to recognize 1,000 of classes. And if we take a moment to recap the ingredients of this success, first, the first ingredient is a very large collection of images with annotations. One of the most famous such collection is ImageNet, that is around for quite a while now, and that is in the order of millions, and every single image is annotated. Then you need very deep neural networks. You can go for alternatives, but still the trend is to go with very deep networks with many parameters. And on top of that, you throw lots of compute time and resources at your problem. And you can build a very good image classifier. And now, if you would like to classify one of the 1,000 categories of the ImageNet dataset, there are already extremely strong models pre-trained that you can use. And that's extremely convenient. But what happens when a new problem comes along? Let's say that now you would like to classify famous landmarks. Then you have to do that over again, you have to collect a large collection of images. You have to train your model from scratch. Again, this has a cost in terms of computations. And yet another problem comes along. So let's say that this time you're interested in paintings, entirely new domains, and you want to classify, I don't know, as styles or painters. You have to do that again. So you have to see, you have to collect these images, you have to train a model. And again, that has a cost. So dealing with every new problem from scratch sounds like a giant waste of time, of memory, and of resources. So can we do something else? And this is exactly what lifelong learning is about. So this is the research topic that considers that the task you're going to solve is not seen in isolation, but it's part of a larger set of tasks that you're interested in jointly. And we would like to leverage the relations between these different tasks. So learning for one task helps learning for the other. And there are many exciting problems related to lifelong learning. So I won't have time to cover all of them, of course, and we haven't studied all of them either. But I'm going to give you a few examples and show you what we've done on this topic. So let's consider only two tasks for now. Let's consider that we have task A and task B, and we're wondering if task A can be useful for task B. Then we have these two questions that arise. How should we train for task A so it will transfer as well as possible on task B? And once we have a model for task A, which adaptation should we perform so it's useful for task B? And now we will go one step further. We would like to use the task A as a proxy task and train a model for visual representation that by design is going to transfer well to a still unknown class, unknown task that will come along in the future. So we don't know what's coming next. That's why we want to pre-train a visual representation that will transfer. And this task A is just a pretext task to build visual representations. So this brings me to the first part of this presentation, that is about looking at training transferable visual representations. And actually people have very quickly found out that models that are pre-trained on ImageNet with its labels using fully supervised classification are producing extremely good models that are strong starting points, so that are producing good visual representations that can be leveraged to other tasks for which you have maybe smaller sets of data or fewer annotations, such as a different image classification problem, or object detection, or instance segmentation, or image retrieval. So that's pretty convenient. ImageNet is an excellent starting point if you use it, images and annotation all together. Yet, assuming that a fully annotated ImageNet size dataset is available for your problem of interest is a very strong assumption. So what can you do to make this more approachable for other domains? And it would be very interesting to be able to reduce the annotation cost that is associated to this proxy task. Because remember, right now, proxy task is fully supervised classification. So can we reduce the amount of annotation that are required for pre-training this visual representation and still have representations that transfer well to different tasks? And I'm going to show two of our recent contributions towards this goal of reducing the annotation cost associated with the proxy task. The first one is on self-supervised learning, and the second one is on weakly supervised learning. So let's start with the first one that we have presented last year at the NeurIPS conference. And it was in a paper entitled Hard Negative Mixing for Contrastive Learning. So remember, the goal is to train transferable visual representations. And the standard way to do this is to use fully supervised classification on ImageNet. And this requires each image to be annotated with one label among 1,000. So this requires fine-grained annotations produced by experts, because not everyone can get the exact class of a mushroom or of a bird or of coral right. So is there a way we could train visual representations but without any annotation, just with sets of images. And this is something that we can approach with self-supervised learning. So self-supervised learning, in the definition, I will use it here. These are learning approaches that are unsupervised, but still they borrow from the supervised techniques, except that in this case, the labels, they do not come from human annotators, but instead they're fabricated from the data itself. So I'd like to give you some examples of what self-supervised learning can achieve for visual representation learning. And I will start with one of the early approaches. This one is based on context prediction. So if you're given a patch that is extracted from a mini image, for example, the patch of this cat face, and then a second patch that is extracted in its surrounding, the model is asked to predict the relative location of the second patch with respect to the first one. So as you can see, this is taking a decision among the 8 possible positions if you discretize. So this is a classification problem, except that the labels are not coming from human annotators, but the labels are automatically produced from the data. And by learning, well, by training a model to get this task right over thousands of patches on thousands of images, it turns out that the model you produce is a very good starting point for visual representations. And I'm going to give you a second example that is a bit more recent and I find very interesting because of its simplicity. If you take an image and you predict and if you take an image, you produce the different possible orientations of that image, and you ask the model to predict which one is the correct one. Again, classification task where the labels are fabricated from the data. And by training for this task, you actually obtain a model that is, again, a very strong starting point to solve other classification problems that are at the level of the categories. So you're starting from something that sounds very image level, and this is useful to tackle more complex and more semantic tasks. And there are actually many self-supervised learning approaches that have been proposed to train visual representations. And I cannot go over all of them, but I can only encourage you to check some of the survey or the excellent tutorial from Andrew Zisserman if you're interested. I will directly jump now to what is one of the mainstream approach nowadays to tackle self-supervised learning for visual representation. So now the dominant approach is based on contrastive learning. And there are many approaches following that route, and they more or less are based on this exact same intuition that I'm going to describe now. You start from an image.
Établi via une plateforme d'échange et d'expérimentation entre professionnels. Donc, actuellement, il y a une quarantaine.
Est-ce que vous pouvez éteindre votre micro?
La blockchain, l'IoT ou la sécurité. Et donc, maintenant, déjà en 2019, la FNOR avait initié cet atelier autour de comment sécuriser les relations contractuelles. Je ne sais pas qui c'est.
Bon, okay. Ils sont arrêtés.
Je pense que je l'ai trouvé.
Ok, merci.
Merci.
Désolé pour l'interruption, Diane.
No worries. So yeah, I was talking about contrastive learning for self-supervised learning of visual representations. And okay, so the typical approach is to start from an image. Here again, we're taking an image of a cat. We apply standard image transformations that people use for, let's say, data augmentation. So this produces 2 different, potentially visually very different images of the exact same instance. Here, this part of the cat. And now we would like to train a model to represent these 2 images in a way that the 2 obtained representations are close to each other and far away from the representation of another image. For example, this image of a dog. And of course, you do that not with a single negative image, but with many. And here I'm using the image of a dog, but if you would take the image of a different cat, this would also be considered as a negative because we have no way to know which are dogs, which are cats, because we're not using any labels, remember? So this is a very dominant approach. And at the time of this work, the main ones were MoCo and SimClear. So they're all based on they're both based on this framework. And our work is built on top of MoCo, but that doesn't really matter because we could have built that on another one. Now, a clear observation that has been made by several previous papers, and that we also observe in practice in our case, is that making the proxy task more difficult actually leads to visual representation which generalize better. So how can we make the task harder? Well, there have been already plenty of attempts. One thing you can do is to create better positive pairs. By better, I mean more challenging. So that would be more challenging version of the same image by handcrafting really difficult and very different versions of the same image by tweaking the data augmentation. And this is one of the contributions of the MoCo paper. Something else you can do is to build better negatives. And SimClear is doing that by increasing the batch size. And by increasing the batch size, as a side effect, you have more negatives. Or you could also increase the memory size. MoCo doesn't increase the batch size, but keep track of a memory bank layer to have more negatives. And that works very well, except that after a few epochs, you notice that most of the negatives you obtain are easy. And by easy, I mean they have almost no contribution to the loss or no contribution at all. And only a few hard negatives do have a contribution and help the training. So how do we make sure that we continue training and we have still hard negatives to learn a better representation from? Well, in our work, what we propose to do is to create artificially hardest negatives by composing from the hard negatives that still exist in the batch. So one thing we can do is to mix two negative samples, or we can mix the query with a negative, but that's something that we can do directly in the feature space. We don't need an image that produces that feature. We just generate a feature that by design is negative and is going to have a contribution to loss because it's constructed to be a difficult negative. So this means it can be done on the fly at train time with a very small additional cost. This is what we proposed. And this is the mixing of contrastive hard negatives, or MOCHE in short. And I won't have time to go into the details of what we've done, but experimentally, we have shown that MOCHE is making the proxy task more difficult. And MOCHE also better uses the embedding space. So we observe that it generalizes better to new tasks. Actually, it trains faster than MoCo, and it's built on top of MoCo, but it trains faster, probably because of these hard negatives that boost the training. And for some transfer tasks, it's even outperforms a visual representation pre-trained the standard way with ImageNet and its labels. Now I would like to jump to the second contribution in the direction of reducing the annotation cost. And this time, instead of using a self-supervised approach, we are going to use companion text that comes with images. And that work we presented last year at the ECCV conference. So if you remember what we're trying to do here, we want to pre-train visual representations that transfer well. And we would like to reduce the annotation cost. So the standard approach is using ImageNet with its labels and using fully supervised classification as a proxy task. We've seen that at the very end of the spectrum, we have self-supervised approaches that do not need any annotation whatsoever, but they're still computationally demanding because typically to express their full potential, they need very large training sets, at least in the order of the ImageNet size, so more than 1 million and sometimes even larger than that. In this piece of work, we're trying to find a compromise. We are going to allow for some annotations. Here we're going to assume that the images come with some captions, but we want to be able to work with much smaller sets of images, 10 times smaller. So captions are pretty convenient because you could assume that in some cases you could automatically collect them, for example, from large corpora of text that are illustrated, or you can even ask for specific annotations, but captioning doesn't require expert knowledge. And I'm going to treat that as a weak annotation. Our work takes inspiration from one of the recent advances in natural language processing. I don't know if you're familiar with the mask language modeling task that has been proposed. It works as follows. If you take a sentence, you mask a token, and then you try to predict the mask token. And just by, so this is a self-supervised learning approach, but for text. And by predicting this mask token, we can actually train a very strong language model if you do that on very large corpora of text. So this task is one of the losses used by the famous BERT model that you may have heard of, that is used in NLP. So we draw inspiration from this, and we extend it to image caption pairs. So for training, we assume that we have an image, a caption that describes that image, and we're going to mask a token in the caption. And the goal is to predict the mask token using the remainder of the caption, but also the image. So how do we do that? Well, first, we hope that by doing so, the model is going to leverage the image and find the missing information in the image. So this is going to force the model to learn a strong visual representations. So now that we have defined the task, that is image condition mask language modeling, now we need an architecture to solve it. So for that, we need two things. First, we need a very strong visual representation, right? And this is what we want to learn. Everything else is a pretext. Remember, this is a proxy task for learning visual representation. So we just need to train this visual representation. We have no information about it at the beginning, so we train it from scratch. Then we need a text representation. For that, there are very good text representation out there. So we use a pre-trained one, such as BERT, and we freeze it during training. And then we need several auxiliary modules whose only purpose is to solve the proxy task, to predict the mask token. So what do these auxiliary modules do? Well, they're supposed to align the representation so the semantic information coming from the visual image can align with the semantic information coming from the caption. And ideally, we would like the representation to be able to focus on the image regions that actually correspond to the mask token. So that's what we propose, right? This proxy task of image condition mask language modeling, or ICML for short. And as the byproduct of the training for this proxy task, we obtain a visual representation. Again, I'm not going to go into the details of the experimental evaluation, but we observed that ICMLM is comparable to the self-supervised learning approaches that were available at the time, using 10 times fewer images. We use in the order of only 100,000 instead of 1 million. And ICMLM is also closing the gap with fully supervised training with classification using ImageNet and its labels. And now if we look at the visual attentions that are produced by our model, we can see that as we mask different tokens, the representation that we obtain, we have an attention maps that focus on different regions of the image that correspond to the mask token. And you can see on the right the different predictions that are produced by the model. So this brings me to the last part of pre-training visual representation. And I don't want to talk about any contribution, but I want to discuss how these visual representations are evaluated. And I want to show you a study that we run to evaluate how well these models transfer to new classes they've never seen. So again, we assume that we have a proxy task that is used to train a visual representation. So the standard way to do that we've seen is using fully supervised classification on ImageNet and its labels. And that's something you may want to evaluate, but you may want to evaluate as well something that is less annotation hungry, such as the different approaches we've seen before. And that produces a visual representation that we want to evaluate. But we don't know in advance which target task we're going to use it for. So we don't know if it's going to be classification, on which objects, or something else. So how do you know beforehand that you've produced a good visual representation? that you will generalize well and that you will apply well to the task of interest that you still don't know? Well, typically, the approaches proposed in papers are evaluated in as diverse target data set as possible. And the idea is to often use many domains, many problems, such as classification, but also detection and so on, and many types of objects. But, that's good, right? Because this already gives you a first and good intuition on the capability of visual representations. But we wanted to formalize the evaluation of visual representation. And because we formalized it, we had to narrow down the exact research question we're looking at. So we narrowed down the evaluation to concept generalization. So when training a model on a set of seen concepts, so these are the only object categories or other types of categories the model has seen when training the visual representation, how well does your visual representation generalize to new unseen concepts? So in other words, does learning about cats is going to help you learn faster about caticorns? How well do you transfer? And to answer this question, we proposed a benchmark, a concept generalization benchmark that we called COG. And to be able to build such a benchmark, the very first thing we had to do is to be able to measure the semantic distance between two different concepts, between two different categories. Because obviously it's easier to generalize from tiger cat to European wild cat than from tiger cat to cabbage worm. So how do we measure the semantic distance? Well, we relied on something that is fairly standard, that is the lean similarity that is used in the word graph. And to measure the similarity between two concepts, we actually measured the semantic similarity between their corresponding nodes in the WordNet graph. And we compute this lean similarity that requires to look at the information, content of each node, but also the least common subsummer, which is basically the ancestor. So once we have this semantic distance, we can rank different categories from the closest to the further away according to the semantic distance. So intuitively from the easiest to transfer to the most challenging to transfer to. And now we would like to generalize this for our benchmark to a distance not between single concepts, but between sets of concepts. So we can build a full benchmark. So how do we build our benchmark? First, we need to find which data set to build the benchmark on. And if the only thing, if the thing we want to evaluate is concept generalization, then the only thing we need to, that should vary are the concepts themselves. We don't want the image distribution to vary. We don't want the way annotators have annotated the data to vary. So the perfect way to do that is to create everything from a single giant data set. And luckily that exists in the ImageNet dataset. And I'm not talking about the 1000 class that people standardly use for training and evaluation, but I'm talking about a full ImageNet that is actually 14 million images and more than 20,000 categories. So that's our starting point. Then we select the 1000 categories that are standard from the ImageNet 1K that has been used for the challenge that everybody knows to be our scene class, because most of the models are trained on this data set anyway. And this is a subset of the big one, right? And then we built 5 sets of 1000 categories. All these sets are fully disjoint that are of increasing distance from the original ImageNet 1K. So this allows us to have a well-defined training set with 1000 categories and 5 different test sets that are of increasing difficulty that we're going to call concept generalization levels. So this is how we build the full benchmark. And I don't have time to go into the details, but we ran a full study where so far we've benchmarked 28 different approaches, including different architectures, different proxy tasks for self-supervised learning, visual representations, different regularization approaches. And among our main conclusions, we've observed that it's harder to generalize the semantic distance. It's harder to generalize to semantically distant concepts, which was the founding assumption of our work. So this is as expected, but we verified that it's indeed more challenging to generalize to more distant sets of classes. And interestingly, the self-supervised approaches that tend to generalize better to these unseen classes that are more challenging. This brings me to the summary of this first part, where we were looking at pre-training visual representations that generalize well to still unknown tasks. And we've seen two different ways to reduce the annotation cost for this pre-training, one based on self-supervised learning and one based on weakly supervised learning. And we've seen also a principled way to evaluate concept generalization of these visual representations. Now I'd like to go back to lifelong learning and this relation between tasks that we study. For now, we've looked at different tasks. And I would like to change a little bit what we're looking at, but instead of assuming that the domain stays the same and the task changes, we're going to do the opposite. So we're going to look at domain adaptation, and more particularly continual domain adaptation. So here we assume that the task we solve is the same. If we're classifying a certain number of categories, we are going to still consider the same categories, but we would like, when you change a data distribution, to be able to transfer from one domain to another. So this is what domain adaptation is about. And continual domain adaptation is when models should be able to adapt as new data distribution comes along without forgetting too much about what's happening before. So let me explain in detail what I mean by that. So first, what do I mean by data distribution? Maybe your first domain is about natural images. Then the second domain is about paintings. So you have your first model trained on the first domain, and then you adapt it by, for example, fine-tuning on the second domain that is about painting. And maybe then you encounter a third domain that is about pixel art. Your model adapts sequentially, and there are extremely good ways to adapt from one model to the other. But something that is quite intriguing and still well known in the community is that once you've gone through these different adaptation steps, the final model you obtain, if you apply it back to the previously encountered domain, your model has almost entirely forgotten everything it has seen before. So the model, after going through all these updates, is really bad at classifying natural images again. So that's the problem we're going to look at next. Catastrophic forgetting, this is how we call it. And this has been known for a while, but this is still a real problem when we're doing adaptation of models from one task to another or from one domain to another. So let's discuss about avoiding catastrophic forgetting. And I'm going to deep dive in one approach that we've worked on. This is the most recent piece of work that we have. And we're going to present it next month at the CVPR conference. And this is about continual adaptation of visual representations using meta-learning. So maybe many of you are very familiar with domain adaptation, but just in case, I will recap what it is about. This is a standard problem which arises when the distribution of your training data is very different from the distribution of the test data when you're going to deploy your model. So to take a concrete example, if you train a robotic platform in simulation, maybe when it's confronted to a real environment, unexpected problems arise and you have to adapt and cope with these unexpected problems. Let's take a second example that will follow us for the rest of the presentation. And let's assume that we have a self-driving car that has been trained in a urban environment. And suddenly it's moved to a countryside road with lots of snow. Then it probably needs to go under some retraining. So this means that you need to adapt the model. The adaptation can be fully supervised, it can be semi-supervised, it can be unsupervised, depending on if you have labels or not. There's many techniques that exist depending on if you have lots of target examples to adapt from or not. And I'm not going to give you more details about this. There's an excellent survey that Gabriela Churka has wrote, and it's part of a book, so I can only recommend. But what we're going to look at today is the question of continual domain adaptation, where we assume that our model sequentially updates as new data comes along. And we would like our agent to continuously adapt without forgetting previously learned information. So how can you do that? There's a naive solution that is simply keeping track of all your training examples since the very beginning for all the domains you've encountered and retrain the model from scratch every time. So you're going to keep track of all the domains, retrain over and over again. And that works extremely well. But the problem is that in terms of time, memory, and computation, it's extremely costly. So this is really intractable for a real application. On top of that, maybe it's not possible to keep track of all your training data since the beginning for privacy reasons, right? So what else can you do? And that's the framework we've decided to work on. How much can we mitigate forgetting if you don't allow any access to past data for retraining? What can you do? And I'm going to present this continual domain adaptation approach without meta-learning. So in our framework, as I said, in any point in time in the sequence, we have access to a single domain, the current domain we're training for. We don't have access to the past. We don't have access to the future. So we cannot retrain for not forgetting what has happened before. And we have no idea what's coming next. So what can we do? Well, something that, so maybe these are examples of domain that are coming next, but we don't know yet. So what can we do? We can already try to diversify the current domain using standard data augmentation techniques. So we can apply standard transformations, and we apply the same transformation to the entire set of images, building different transformed data sets that we're going to call metadomains. And if we're lucky enough, maybe one of these metadomains is close enough to the next domain we'll encounter. So it prepares for a better adaptation and mitigates forgetting. So that's the first thing you can do. You can enrich your training set. And by doing so, we hope to bridge the gap between the current domain and the domain you'll see in the future. And actually, we experimentally observed that domain randomization, that's how I'm going to call it, generalize really, really well. So it's a surprisingly powerful baseline. But now we are going to leverage this metadomain in a slightly more principled way. So in the approach we developed, we have the exact same first step. We are going to create multiple metadomains using domain randomization. So we have our domain. We have several metadomains that are, we can see them as fabricated potential other domains we could encounter. And now when we are training, we are going to consider three aspects for training. First, and foremost, we're going to train for the current task because we want to train for this domain because we're interested in this domain and we should leverage the data we just acquired. So we train in a very standard way. But at the same time, we are going to train to adapt faster. We don't know what to adapt yet because we don't have access to the future domains. So we are going to use these metadomains to simulate what can come next. And to do this adaptation, we're using the meta-learning approach of the MAML paper proposed by Chelsea Finn and colleague. And the intuition behind is that you train your model parameters. So after doing the current update for your current model, you make sure that it's also a good model that is going to adapt well to your potential next domains, which are here our metadomains. So this is what this fast adaptation with meta-learning is about. And at the same time, we are going to train to mitigate forgetting. So how do we do that? We have yet another part in our loss, and it's going to consider that you do one learning step in the current model, and you're going to test, and you're going to do one learning step for your current model on the meta domain, which is potentially your simulated next domain. And you'll see how much this step is going to make you forget about the current task. And you minimize for this forgetting. So this is what we're doing here with the mitigate forgetting part of the loss. So we combine these three things together, and this is how we train the model for the current domain, faster adaptation, and mitigating forgetting. And what I find interesting about this method is that everything happens at train time. But once you have applied your enhanced training, you still have a standard model. So it can be directly applied to the text domain in the sequence. You don't have to keep track of samples from your current domain. You don't have to keep track of hyperparameters or other parameters. It still works with a very standard model. It's just the way you've trained it that is slightly different, because it has used this meta-learning strategy. And actually, you can do that for all the training of your entire sequence. So as you encounter new domains, you can train your model in this way for every new step in the pipeline. And when you deploy your model, you can test on every single of the domain you've encountered during training. I'm not going to give you experimental details again, but our experiments show that, as I mentioned already, domain randomization is an extremely strong baseline. So that's really nice to observe that this is very powerful. And we've seen that meta-learning indeed allows for a faster adaptation and some resilience to the sequential domain shift that happens during the different training stages. So this brings me to the end of my presentation. So again, I'd like to advertise for our share, I share on lifelong representation learning. If you're interested in some of these works, I've put the references again. And of course, none of these contributions would have been possible without my amazing collaborators. So I just would like to spend some time thanking them. So there's Brilliant Sareldes, my PhD student, co-supervised with Yanis Kalantidis and Kartika Alari. My colleagues from Naval Labs, Ricardo Volpi, Yanis Kalantidis, Grégory Roger, Philippe Weisenfeld, and Julien Perez. Collaboration with Kartika Alari from INRIA. And I would like to thank also Noé Pion, who interned with us last year. Thank you very much. And yeah, I would be very happy to answer any question about this work.
Okay, thank you very much, Diane. So I think that for question, we better go with directly asking questions for orally asking questions to Diane. Maybe Rufin, you can start. You had a question that was already answered by Mert, but maybe you can ask again,
so just
push you a little bit on this.
Sure. As a reminder, the question, it was very nicely answered, but maybe you want to add something. I was wondering, this IC-MLM model sounded very much like what they did in Vertex, except that it wasn't a masking objective. And also it's related to CLIP, which was thoroughly tested for transfer learning, few shot, zero shot learning, etc. We were wondering if you also tested this IC-MLM model on these sorts of transfer learning tasks, or if you compared it, let's say, to Vertex, etc. And your student nicely answered this, so I don't know if there would be much to add to this.
It's up to you. I haven't seen the questions and the discussion happening in
Sorry,
chat.
yes.
So I'm trying to catch up, but I don't have time to read. So indeed, you pointed to two extremely related piece of works. So Virtec is it's a work that appeared more or less at the same time. And it's extremely similar in the intuition, and they also train on very similar data sets. So it's very, very close. There are a few differences in the loss that is used for training and the architecture also. But that's, yeah, we could have compared at some point. I don't think we have the actual comparison because that was not out there when we worked on this. CLIP is bringing that to an entire new level. So again, same intuition, learning visual representation from scratch with caption notation, but they have, well, in our work, we wanted to go for fewer images, right? Instead of 1 million, we go down to 100,000. They go to a few 100 million images with captions to train. So I don't think what we proposed would scale. We don't even have the data set anyway. And, but they have a very interesting loss. It's an interesting piece of work. And yeah, all three are very related in the motivation for, yeah, I think text is a fantastic source of annotation that is probably underused because even if you don't have perfectly captioned images, even noisy text can be extremely useful. And yeah, I don't know if that answers the question. I'm sure
very well. Yes,
Bülent answered even more clearly in the chat. So, yeah.
Thank you. Joel, nice to see you here. You also had a question. Maybe I can let you raise it orally.
Hello. Thank you for the presentation. I would like to know if learning for multiple tasks or domain lead effectively to bigger models than for each individual task. I have an intuition that if I need to do a lot of different things with a lot of different data, I will need bigger space to store everything. Is it the case?
Yeah, that's a very good point. And lifelong learning is extremely rich, and there's so many ways to approach it. Here, we really made the assumption that we have a well-defined sequence of tasks. But if you know that you want to solve many tasks in parallel and you want to do multitask training, this is probably an entirely different paradigm. And so that's not something I covered today, but there are extremely good works looking at that. And we can go into the details, but like as a general answer, I guess that's also the point of your question. There's no free lunch, right? If you want to be able to cover a very large number of domains and a very large number of tasks, maybe one single unified model will not answer everything, unless it's really huge. So there's also this research direction that we hope to get to very soon. If you have a very large number of classes, which groups of classes go well together and can be learned jointly, and in which cases should you have multiple models to deal with these very different classes of approaches, right? So that's still a very open question and very interesting direction to look at. There are hybrid approaches that enrich the model with some generic part and some task-specific components that you can enrich as new classes come. There are very different ways to approach this that all have their pros and cons, and yeah, depends what you can do, if you can store data for retraining, if you have constraints on the size of your model. I hope that answers the question.
Maybe about specifically the multiple domains, the models that you self-trained. Did you design them to be specifically a little bigger than for that if you didn't have to retain every information, and that, for example, the part about not forgetting what you had previously learned? Did you design the model to be a little bit larger to account for that? Or did it not take part in your design?
So for all the experiments we've conducted for that piece of work, we used the exact same architecture for the baseline and for a proposed approach. So they have the exact same number of parameters, and we use a very standard model because we really wanted to test it on a very standard architecture. So it's basically a ResNet. We could have tried to enrich the model to store more parameters, but that's not something we've looked at.
Okay. Thank you. So it means it can actually work with the same number of parameters.
That's exactly the framework where we tested it, because we wanted to change only the training part, but that the model could be a very standard model, something that you would train the standard, like something you could take a pre-trained ResNet or whatever you want, and then you just like fine tune it differently to mitigate forgetting.
Okay, thank you very much.
Thank you. Cesar, I think you have a question, at least you are raising it.
Thank you. First of all, Diane, fantastic presentation. You know, I love not only the content, but the way that you presented it. It's extremely easy to follow, you know, and I think you are able to convey those big ideas very well. And my question, you know, is it's about one of those big ideas you showed through your work, that there are a lot of benefits on the way in which you prepare and pre-treat the data when it comes to training. You know, there are a lot of benefits of, you know, like creating these automated labels, on, you know, rotating the images and so forth. And I'm wondering, you know, in those models in which you achieve better results by pre-treating the data in smart ways, do you only get models that are more accurate, but also when it comes to, you know, computer vision, there has been a lot of conversation about fairness and bias. Do you get models that are less biased or that behave better in those dimensions as well? Do you have any intuition about that?
So that's a very good point, and that's a difficult question, because it's so we know that the models are biased, and we know that supervised models are biased, and we can even inspect some of the bias in the labels. But we also know that self-supervised models are biased as well, and it's even more difficult to keep track of how they're biased. I don't really have a very strong intuition on where we stand there, because we probably need a proper benchmark to study these things. And my intuition is that we should probably also train in a way that, yeah, there's different kind of bias, right? That terms is so loaded, but there are easy bias to look at, such as texture and colors, and that we can study. And there are many approaches that have shown how to reduce that bias. There are more problematic bias, especially when we're working with text, because we put special meaning behind words. I think that's something that we should really pay attention to, and I don't think I have the right answer, and nobody has the perfect answer for that. So I don't think self-supervised learning is less prone to bias. I'm not sure it's more prone either, not by design. I wish I could make a very strong statement about what we know about our models, but I think we need to work on that carefully, because it's a very interesting and very important problem.
Thank you. Great answer.
I mean, just sort of along the same lines, Nicola, if I can butt in, or maybe I shouldn't.
No, I was looking at my mic to ask for your question, Nicolas.
Okay,
Well,
so no, I've also been thinking about sort of things like the robustness of these models. I mean, I would imagine that when you start looking at these meta-learning questions, you know, you might have some interesting epistemological strategies to encode there. I mean, you looked at this randomization, but surely there are others that might lead us to think about being robust on relevant properties, and you know, on the sort of not letting irrelevant properties bias us, and getting but being sensitive to relevant properties. What I don't know, I think this idea of meta learning is quite interesting, and I would imagine that it'd be interesting to look at various formal epistemological approaches, theories, and constraints here. You just looked at a kind of simple one, but probably you've thought about this much more than I have.
So if I understood the correction, you're asking if the transformation we apply to build these meta domains if they're all relevant and if the way we choose them have a strong impact on how we, well, how the approach performs, right? Is that correct?
Yeah, yeah. I guess my question was more nebulous than that. That's a nice precisification of the question. My idea was that you know, we have a lot of problems. It's sort of related to Cesar's question. We have a lot of problems with robustness in image classification, and it seems like some sort of meta learning strategy would be the right way to go to attack this problem. That was the gist of my question. I just wondered what you had any thoughts, whether you've done any work on that, and actually how these kinds of, you know, this domain randomization, did it do anything with respect to robustness?
Robustness to the domain shift or robustness in general?
Well, robustness to the classification task. So, I mean, did we get away from the problem where, you know, changing 3 pixels and, you know, we get a catastrophically different prediction?
Right. So I think there's many good points in that question that I'm not sure I will manage to cover all of them. I think when you talked about changing this few pixels, you are talking about adversarial attacks.
Yes,
which
yes,
is
of
something
course.
we haven't considered.
Yep, sorry.
Because
yeah.
the initial motivation was to really look at domain adaptation when domain changes, and we had a very, well, let's say computer vision view where we start with image, like natural images, and we go to sketches, and then we go to I don't know, paintings, and we see how bad it goes back to the natural images. But this is true that meta-learning can help being resilient to much more than just the domain shift. For adversarial, I don't know. I don't know well enough about these adversarial attacks to answer that properly. But I think meta-learning is a fantastic tool. I think we're just scratching the surface with what we've done. Chelsea's Fin group has done amazing things with meta-learning for reinforcement learning that probably also go very much in this direction of robustness understood very broadly. In our case, if I try to go back to the very first part of the question, I think this is true that what we've done is a bit limited in the sense that we have handcrafted transformations. So we have used priors on the kind of transformation we expect from one domain to another. I'm sure if you have more prior information, you can build your meta-domain in much smarter ways. Mm-hmm. Maybe have not like generated metadomains, but real metadomains that are coming from whatever data you have access to. And maybe that's a way to construct them so they really build the kind of robustness that you would need for a particular problem. But we are really at the beginning of this catastrophic forgetting study. So
yeah, it's very interesting. I think it's also very interesting. I think we need to do similar things in NLP, where I think the results, masking is a nice technique, but we have just terrible troubles with inference once we go beyond a single sentence. And anyway, so I'm thank you for this insight on meta learning and your discussion. Thanks.
Okay, so I think we are good for this hour of presentation and discussion. So thank you very much. Well, first, Diane, for your excellent presentation. Thank you all for interacting and questions. So now you have one direct connection to MII, and of course you're welcome to use it and go to Diane and her chair and her lab to have more details and start collaboration. Thank you all. Diane, maybe we can continue the discussion on the other link that I sent you, and well, see you all later.
Thank you very much again for a great discussion and for the invitation.
Thank you, Diane. Bye.
Thanks a lot. Great.
Great presentation. Thanks.